So we continue. This is a live code session. Let me share screen with you so you can see my screen, right? Yeah, you can see the screen. You are screen sharing. It says I have only one screen, so you must be able to see. Anyways, so the code is from here. I'm going to share the code. There's this GitHub repository. Actually, it's a very strange type of a code because this guy, the owner of the repository, is working on different types of machine translation codes, and he has many libraries in different projects. So in order to be able to make a project out of it, I had to collect different parts and different functions from different projects. Because in this example, what he's trying to do is he's trying to do a machine translation from a language to another language. Which language? Actually, you can pretty much easily change the language because it's using a library called Torch Text. It is the main NLP library of PyTorch. And you can download English or Deutsch, German. In this example, that's what I'm doing. I'll be translating from German to English in the guy's example. And the nice thing is, he also has a blog explaining what it's doing. So I think this is a very nice place to start a machine translation journey. As again, I want to repeat what I said in the previous hour. This is not a deep NLP course. We have a deep NLP course of Tuba Hoca. And Tuba Hoca is going over these subjects, particularly the subjects, in quite detail. So this will be maybe the only NLP example we are going to be working on. And it's going to be simple because this is just, I'm going to be covering in a couple of minutes, an LSTM, fed to an LSTM encoder decoder architecture, where you translate one German sentence to an English sentence. So the network architecture will be very simple, an LSTM, another LSTM, and a fully connected layer, nothing else. And it's going to provide us some results. However, in NLP literature, it's quite more complicated. However, this is a very nice and simple example for us to understand the current encoder decoders. However, although the architecture is very simple, manipulating NLP data is not that simple. However, using the libraries like PyTorch Text, it becomes very easy. I mean, in Torch Text, you can automatically download using a library called Spacy, download some tokens, which are actually words of a language. Okay, there are different languages. Unfortunately, there is not Turkish. I wish there was, but in Spacy's vocabulary, for now, we don't have any Turkish. But there are different libraries for Turkish. I mean, you don't have to use Torch Text. If you're into NLP, that's why before I start recording, I asked you, any of you using NLP in your projects or not. That's why I asked. You need to get familiar with manipulating data, text analytics, using at least one library like Torch Text. And Ozan said he's doing it. He's doing it in his thesis, and he is familiar with that stuff, so there's no problem with him. But if you're not, but if you want to delve into it, maybe Torch Text and this example is a good idea. Anyway, what is Torch Text? It's the data module that provides a pipeline for processing your data, extracting word embeddings, batching, and preparing it for training, and simply a loader. That's in PyTorch, they are called loaders, you know. And you can create different objects to represent your vocabularies of that language. So it is what it does. I mean, I was currently debugging it. So you load these libraries for the first time. You need to download them somewhere. It's like this. I mean, I've done it in my terminals in Anaconda, whatever. So it creates two languages, like German, which is German. It's a torch text field object. And it has this vocab object. And when vocab, I've left some comments here. So if you get vocab breaks, you'll get the frequency of each word in your vocabulary. And actually in this vocabulary, we have only this number of examples. This number of examples. So it downloads from Spacey a German corpus, and the corpus has 5,000 something different number of German words. This is not the number of words in German language, but it is a representation of German language, and it covers most everyday words. Okay, and when you're loading it, in this example they use the build vocab example, and build vocab example is an example this guy written himself. It creates that field, and it has very nice interfaces. For example, the interface this guy has is make it at most 10,000 tokens words, and if it is more than that, you can leave the words with frequency less than 3, but somehow the words in this vocabulary is less than 10,000, so it also gets the words which has only one frequency, which we come across in the corpus only once. It also keeps it because this number, the total number of words in the vocabulary, is less than 10,000. And please note that in this example, it does use a very simple embedding, the so-called one-hot vector embedding, which means we are representing each word just like the example in Andrew Van G's sequence model course. So let me just show it to you. So these are the words. For example, I'm going to go over the top of the list. So the first word is dot. The second word, it is treated as a word because it's the end of sentence word. And the second one is ein. I mean, if you're familiar with German, it is an article. Well, articles are male and female, so there is I, einem, einer, eine as well. But ein is like a article, word, letter A article. So how is it represented? Since it's the second one, it's sorted here. What this guy does is it represents this as a one-hot vector. Okay, so this is ein. Well, this is how this example converts words into vectors, because in the end, we are going to be feeding them to an LSTM. And LSTM, as you have seen in the previous weeks, is a neural weight multiplier with an activation function and a recurrent connection. So it will need numbers. So the way we convert these words to these vectors are called word embeddings. And there are different ways to embed words, guys. For the sake of simplicity in this example uses one hot vector. There's one hot, which represents the order of the sentence in the frequency table, and the others are 0. As you might imagine, for the other sentence, which is einem, it's going to be not this one being 1, this is 0, and the second one is 1. So it will be like this one 0, this one 1, 0, and zeros for the second one, which is einem here, right? So this one-hot representation is kind of good because it's a categorical representation, and every piece of category has equal Euclidean distance between them because these vectors are orthogonal to each other. And the distance of all these vectors, because it goes to like 5,300 something, which was the length, what was that? 74 this here by 1, because it is the length of the corpus. So you have a very long vector where each category, the token, the word, has an equal distance. This is something good in a sense because we kind of put them uniformly in an independent space. But in a way, it's not good because, in my opinion, in a language, the distance of, for example, in German, the article ein and einem should be, I mean, small compared to a distance of these words to another distance. In English language, you may think of this as the distance between two words, a man and guy, should be less than their distance to the word, I don't know, fork. What I'm trying to say is this is a way of embedding, and this is beyond the scope of this course. We are going to be covering the titles of word embeddings, but we are not going to delve into the details, which is a subject of text analytics. And if you are going to study those subjects in your thesis, I strongly recommend you take Tubahoca's course. But in this example, it is this. So in the end, that distance needs to be learned when you're translating the sentence. That distance is not provided in the word embedding here. It is going to be learned by the encoder itself. The encoder will also learn those distances. It's going to learn that this vector and this vector has a similar, should be similar. It's going to be learned by it. It's not going to be provided by the word embedding. Okay. How it's doing it, it's loading these vocabularies, and these vocabularies is getting ready. It's making the data ready for training. And I'm going to jump directly into the architecture. The architecture will create an encoder LSTM and a decoder LSTM. And if you look at the definitions of it, the encoder LSTM is just a single LSTM. If you look at the forward part, it's a single layered LSTM. It gets the embeddings and provides the embeddings. So it's getting a hidden state and providing a hidden state. And if you look at the decoder LSTM, there's a very simple difference in the forward pass. I'm just going to open the forward pass of it. It's, where is it? Yeah, there's an LSTM. There's a dropout so that we don't have, it doesn't overfit. And it has a fully connected layer so that there's an output layer which will create the word embeddings for the output language, the English language, nothing else. The architecture is that simple. And actually that architecture is being very explicitly explained here. Okay. And actually this block about this code provides details of torch text as well. Again, if you're new to NLP and if you're delving into it, I believe it was a nice place to start because NLP, deep NLP is not my kind of field. You know what my field is. I felt comfortable with this example when I was preparing slides for this course some time back. When I found this example, I was very glad because it's a very simple example. It's a nice place to start. So it explains all the codes and blah, blah. And it gives examples of input-output relations as well. By the way, this is a simple example in the sense that it is an LSTM encoder. In between, we have the internal representation. There's a dropout layer, an LSTM, and a fully connected layer. This is, in architecture-wise, a very simple example. And actually, the problem is also very simple because it is translating from German to English. And the thing is, if you've ever worked with German, I did, they're almost the same language. It's funny for that matter. I mean, of course, there are some sophisticated details in German where articles are different, but in the end, it is not like Turkish and English. I mean, in Turkish and English, the order of words change. Most sentences are constructed quite the same way in both German and English. For example, these examples, zwei Junge, you can immediately get those words, too young. Weiße Männer, white males. Sind, are. Im Freien, outside. In der Nähe vieler Büsche, near many bushes. Slight differences, which can be tokenized into phrases. Very simple. So, which means we won't need large dependencies while we are translating from this language to that language. What we need to understand, I think, I would interpret it that way, is how the internal representations makes out of the parts of the sentence, like where is the subject, where is the object, where is the verb, where is the adjective, is this an adjective, kind of. The internal representation needs that information so that it can construct a proper sentence. That's why this example quite easily trains. And try that on. It quite easily trains. Again, a man in Greenhouse, ein Mann in Grunwald. It's funny for that matter. I mean, in German and English. Anybody who can speak English, I think, can easily learn German if they have the time and the effort to put it. So, guys, the rest of the code is pretty much simple. I mean, you have these, sometimes you have PyTorch training, nothing else. When you have the data loaders properly, which can mini batch your training set, you just feed it to a train loop where you calculate the loss and back propagate. The autograd does the rest. And you know what an autograd is, I'm sure. You should be familiar with PyTorch. So that's it. And in the end, there's a nice thing. It needs to calculate the loss, and we need to evaluate the algorithm's performance with that loss. And when the output is a sentence, the evaluation is a bit tricky, because when you're dealing with signals, just like I do in my entire life, you have some sort of mathematical distance, whether it's an Euclidean distance or a Manhattan distance. However, for text, there are some specific distance types. They are called the bleu distance or the rouge distance, which are French words for blue and red. Different types of distances there. And actually, this guy also has simply implemented them. You can find them, the blue distance. Each distance type in NLP has some character. Some look at the frequency, some look at other things. Again, this becomes beyond the scope of this course. In this course, we don't deal with NLP evaluation metrics and stuff. However, we are going to talk about them, mention them, but if you're into evaluating NLP models and how to perform, if you want to do performance evaluation properly, I strongly recommend you take a text analytics course. So in the end, it provides us these examples. I've just run it for a couple of times, but you don't have to. This block has that nice thing that I did the previous week, because remember the previous week, I've trained the algorithm, and I've taken checkpoints for every iteration, not every iteration, but for some iteration, so that we could see the evaluation of the output. This guy already provides it in its block. I'm going to jump there, and you'll see that it can easily train. So the input sentence is in ein Mann in einem blauen Hemd, ein Mann MN. In einem blauen Hemd, blau means blue, Hemd means shirt, steht means stands, auf einer Leiter, over a Leiter means ladder, over a ladder, and putzen means cleaning, cleaning ein Fenster, Fenster means fence or window, cleaning a window. So a man in blue shirt stands over a ladder and cleans a window. You can see that the sentence is exactly in the same order where the words and adjectives should be. So, and when you do it in Google Translate, it just does it exactly where it should do it. So, and if you look at how it evaluates, so at the first iteration, it's just rubbish because you have rubbish weights. But after the first iteration, first epoch, sorry, so when you go with the entire data set once, the guy, the architecture has pretty much an idea of how to construct a proper sentence. And after the, where is it, 17th iteration, it provides the correct answer for the first time. I mean, so after some iterations, it starts to maybe overfit or oscillate. It happens in these architectures, you know, because the weights are, you're in a dynamic space, you're just running a circles in your search algorithm, the gradient descent, not gradient descent, of course, an advanced version of gradient descent. It was added in our algorithm. And after some point, it converges. So what is amazing about this architecture is, I repeat this, it's a very simple architecture, and it can do this simple translation. I mean, I know translation from German to English is most of the time like single word translation, and almost, not exactly, almost, because the articles change. Sometimes the order of the words change. Sometimes you take them as tokens, because there were examples here. Just if you're into German language, just check these examples. Not all of them are exactly like this. So this Jungen tanzen mitten in der Nacht auf Posten. So boys dancing on poles. Jungen tanzen, boys with mitten is whatever. It's not the right sense. So just if you just work on it in Google Translate, it's not. It does not necessarily. Sorry, it does not necessarily provide you the same output. And I'm going to be doing it for you. So it was in the middle of the night. So as you can see, mitten in der Nacht, so middle of the night, will move here. So the places of the phrases can move, but still it can do this. And actually, this architecture is that the first encoder-decoder model which was provided by Google. So sorry. So if you're into NLP, I strongly recommend you take a look at Torch text and learn how to use Torch text. And you will be amazed by the results of what a simple encoder-decoder, recurrent encoder-decoder can do when it comes to these definitions. That's why we have so many question bots and question answering bots and similar stuff today, because these simple networks work and they don't require many computation. Okay, that's all I'm going to be talking about this example actually. If you have any questions I'd like to discuss, although it's not my entire specialization area, do you have any questions?